This is the third part of chapter 6, dual problems, minimization with problem constraints. Maybe you have noticed that before the midterm we were studying simplex method on programming through simplex method. We were trying to maximize the problem, maximization, but now this is minimization. And before, all the problem constraints were in less than equal form, but now you will have problems in greater than equal form. You will have constraints in greater than equal form. So this is the difference between maximization and minimization. You will be able to formulate the dual problem, and then you will able to minimize the problem. If you are given the cost function, we always try to minimize our cost. Whatever business are we running, that doesn't matter, we always try to minimize the cost. And if you are dealing with the profit, like we did before the midterm, when we were trying to maximize the constraint, maximize the objective function, we try to deal with maximization in case of profit, and we try to deal with minimization in case of cost function. Here you can see that this is the problem associated with each minimization problem. uh, for example, if I try to write same problem in terms of maximization, it would be like profit 16x1, 9x2, 21x3, x1, x2, 3x3 would be less than 12, would be less than 16. And here you can see it is greater than. But here, if it is a problem of, this is problem of maximization, this is problem of minimization. How we can differentiate between them? In case of minimization, you will be given cost function. In case of maximization, you will be given profit function. In case of minimization, your constants will be in the greater than equal form, but in case of maximization, your constant will be in less than equal form. So this is the difference between dual problem or minimization problem and maximization problem. Okay, afterwards, how to deal with this? You will write your cost function as it is in this form. You will write your all constants here, like we used to write in augmented matrix form, and you are given system of linear equations, and we just write them in a matrix form like we used to write. Okay, after writing it into this form, we take its transpose. What is transpose? You have learned this transpose in college algebra. We interchange rows with column. If I change this row into column, it will become 1, 1, 3 and 12. I will change this row into column, it will become 2, 1, 1 and 16. I will change this row into column, it will become 16, 9, 21 and 1. So this is called a transpose of this matrix. Okay, after taking the transpose, here you can see this is the transpose. We write this system back into the equation form. Before, the system was given in x1 form, variables were x1, x2 and x3. Now we will write them back into the equation form, and we will write it in y1, y2. Like this will become y1 plus 2y2 less than equals to 16. Before, initially your constraints were in greater than equal form, that is why it was minimization problem. But since we have already taken its transpose, so now we will write it back into the equation form with less than equal constraint form. Similarly, this one, y1 y2 less than 9, 3 y1 y2 less than 21, and this would be your profit function. And likewise, you can write profit equals to 12 y1 and 16 y2. Before, it was cost function, but now it is a profit function. So you can see that now this is your standard maximization problem. Now we came back to the standard maximization problem, and these are your constants, and this is your objective function which we want to maximize. Now rest of the things are exactly same like we used to do in simplex method. Like we will add the slacks y1 2y2 plus s1 equals to 16. Similarly y1 y2 plus s2 equals to 9. Then 3 y1 y2 plus s3 equals to 21. So this is our profit function. We will write profit function as I told you, minus 12 y1 minus 16 y2 plus p equals to 0. We will write them back into the equation form now. Given a minimization problem with constants, you can see initially the constants were greater than equals form. Use the coefficients and constants in the problem, constant and objective function to form a matrix A. Then we wrote it back into the matrix form and we denoted it by A. In the second step, we took the transpose and we write it back into the maximization problem with constant less than equal form. We perform these three steps and these are what we have wrote here. Formulation of this is called formulation of the dual problem. Okay, this is the fundamental principle of duality. You can call it a theorem 1. A minimization problem has a solution. Your minimization problem will have a solution if and only if its dual problem has a solution. Like we have converted it into a dual problem, like we have converted it into a maximization problem. If a solution exists, then optimal value of minimization problem is the same as optimum value of the dual problem. Now we will solve the dual problem. We will solve the maximization problem like we used to apply a simplex method in the before the midterm. If it will have the solution, then it would be the same solution for minimization problem as well. This is what this theorem tells us. Okay, I have already explained before we were writing slacks with s1 s2 and s3, but in dual problem we will write slacks with different variable with x1 x2 and x3. So this is the only difference. Rest of the things are exactly same. We will write it back into the augmented matrix form with basic and non-basic variables, and we will try to apply simplex method. You can see that here we write basic variables, and how do we know these are basic variables? Because in these columns we have 1 and rest of the elements are 0. In x2 column we have 1 and rest of the elements are 0, and in x3 again we have 1 and rest of the elements are 0, and likewise this p, y1 and y2 are non-basic variables. So we write basic variables on the left side. Now again, as you know, we used to apply in the before the midterm simplex method, the most negative number is minus 16. So this is our pivot column. Now we will divide 16 by 2, 9 by 1, 21 by 1. So the smallest quotient is 8. So this is our pivot row, this is our pivot column, so this is our pivotal element. So with the help of this two, we will make zeros below this 2. So you can see that when we do so, y2, because this was our pivot element, so this y2 will become basic variable. And you can see now y2 is basic variable. We write basic variables here, and you can see in y2 we have 1 and rest of the elements are 0. Now again we start from the bottom row. Which one is the most negative number? Minus 4 is the most negative number, so this is our pivot column. And now we will see which one is pivotal row. 0.85 divided by 0.5, 1 divided by 0.1, 13 divided by 2.5. so this is our pivot row. So this is our pivotal element. With the help of this one we will make 0 above and below, so y1 will move to this position. Okay, so with the help of this one we will make 0 above and below, and we can see that now in the bottom row we don't have any negative number, so it means that we are done with this problem. And we will read the solution directly from here. X1 is 4, x2 is 8, x3 is 0, and profit is 136, which is so called cost as well. So we have now obtained the optimal solution since none of the bottom row indicators are negative. Here you can see that this is our profit. X1 is 4, X2 is 8, and X3 is 0. Minimum of P is 136, which is also the maximum of dual problem. So when profit is minimum, in that case we can say the cost is maximum. So that is how we used to solve minimization problem. Given a minimization problem, these are the procedures. You can see that given a minimization problem with non-negative coefficients in the objective function, write all problem constants in greater than equals inequality. This may introduce negative numbers on the right side of some problems constant. Form a dual problem. Write the initial system of dual problem using the variables from the minimization problem as a slack variable. So first of all, if you have constants, double constant, less than or greater than, first we try to write all the constants in greater than equal form. That is what it tells us. Use the simplex method to solve the dual problem and read the solution minimization problem from the bottom row of the final simplex tableau in step 4. That is what we did in last example. Here we refer to a transportation problem. You can see that a computer manufacturing company has two assembly plants, plant A and plant B, and two distribution outlets, 1 and 2. So if we formulate this problem with all these constraints, it will turn out to be, you can just go through from it, and that would be your problem. So you can see that now some constants are less than, some constants are greater than form, and this is our cost function. First of all, what we will do, we will convert it into a minimization problem by writing all the constants in greater than equal form. If I multiply this first constant with -1, it will become x minus 1 minus x2 greater than minus 700. This constant is already less than form, so I will write it in greater than form, minus x3 minus x4 greater than minus 900. These last two constants are already in greater than equal form, so we will write them as it is, greater than 500, x2, x4 greater than 1000. Now we will write them in a matrix form and we will take its transpose. So you can see that we just did this step, which is written here. Before we can solve this problem, we must multiply the first two constant by -1 so that all are of the type greater than equal, so that we can apply minimization or dual problem form. We will write it back into the matrix form. We will take its transpose. So you can see we write it in a matrix form. We take its transpose, we interchange rows into columns. This row will become column, and this is A transpose. We will write it back into the equation form with y variable, with P. So we write it back into the P form, and all the constraints with less than form because we already took its transpose. So here you can see that now we can apply simplex method by adding slack variable. So it will become y1 plus y3 plus slack equals to 6. Here we will add second slack, it will become equals to 5. Here we will add third slack, it will become 4. Fourth slack, it will equals to 8. So we can now apply the simplex method by writing it back into the equation into the matrix form by adding slacks. So when you will form the simplex method after performing, you will get the result which is written here. You can take it as an assignment. You can perform this simplex method on this. Okay, so the maximization problem will have all the constants in less than equal form and non-negative numbers on the right side. It could be any real number of a coefficient of objective function, and this is simple simplex method. Minimization problem, you will have all the constants greater than equal form, and right side constant could be any real number coefficient of objective function, non-negative. Form a dual and solve by simplex method. That is the summary of whole discussion.